Yeah, hi folks. I'd like to share with you some physical ideas, and that all to do with quantum mechanics and macroscopic items that we can perceive every day. A lot of scientists ask themselves, okay, what happens, for example, in a two-slit experiment? And I just started to think about this subject. The relationship between quantum mechanics and macroscopic stuff. Well, quantum mechanics looks at a particle as a wave-particle duality. So it's actually a wave in space. At this moment, I assume we can only see 4 dimensions. There may be some more dimensions, but okay. Let's assume it's 4 dimensions. So if you look at the universe, it's actually a 4-dimensional wave pattern interfering with itself. And but if it's interfering with itself, it creates standing waves. And that's what we perceive as particles. And so you have a wave and that we perceive as a particle. But that wave particle has a locality, and since it's a wave, it has also some non-locality. So that causes entanglement. It's always that the wave pattern is infinite actually, but it's the main energy is concentrated in a little local environment, space environment. And so, like this. That's what we perceive as a particle. Well, since there are many type of states, vibrating states, you have different particles. And I'm not talking about strings. I'm just talking about that the universe in itself is vibrating. So the 4-dimensional space-time is vibrating. We don't know if there are more dimensions. The question is, do we need them in the first place? So that's the question. But the thing is, if 2 wave particles are, if you send a light beam through a 2-slit, then on the other side, when you have a screen, it hits at a certain pattern, a slit pattern, that 2-slit pattern, in which you see stripes of wave particles hitting the screen, and we know all the things that it's in stripes with certain percentages. But what happens when a particle interacts with that screen? Well, actually, it interacts with another wave particle. So what happens is that 2 wave particles at the screen are interacting with each other. But these particles are different of kind in vibration terms. I mean, suppose you have a light particle and you have a screen particle, an electron, because the light interacts with the atoms, the electrons in the screen. So what happens is that 2 wave particles interact and show interference patterns. At that point, these 2 particles are just adding up as wave packages, and it seems as though the wave particle of the light is collapsing when the spot on the screen appears. But no, it interacts with another wave particle, and that is by adding and subtracting different wave patterns, you get a certain local thing. But the locality of it's just absorbed by the electron, giving off a spot. And at that moment, the locality and the non-locality has merged with the other wave particle, the electrons, in the screen. So it seems as though the wave particle is collapsing, but no, these 2 wave particles are actually added to each other, so that the local energy density is higher, and in the center of that, it's even, if these are the wave patterns of individual particles, then it's even bigger. It's constructively added together, and in other parts it's destructively added together. So that's why it seems as though the wave particle is collapsing at the screen, but that's not the case. It's actually adding two different type of wave particles of the same type of space-time fluctuations, and being added together. Now, what happens if you have two different wave particles being added together? Well, the locality is increasing. The non-locality is decreasing, because the further away, the more subtractive actions are taking place because of the waves are cancelling each other out the further away. Well, that happens if you gather a lot of mass, a lot of particles, then the quantum mechanical properties, the wave particle properties, become more and more particle-like. Why? Because the adding of the wavy aspect, you are adding the wave aspects. So the wave particle properties is only or at best seen if you treat those particles as individual particles, like in a light beam or a particle beam. Then those quantum mechanical effects are the strongest. If you let them collide with the rest of matter, then the more particle properties appear more and more by adding up the wave stuff. And it becomes more local, which is logic because you are adding the wave particles. This sounds a bit funny. Maybe I have to draw it actually. Maybe in some drawings. One moment. Well, I draw in advance some stuff. Suppose you have an electron and a photon, individual. So they are both traveling through space. And the photon looks like this, and the electron looks like this. They have different frequencies in space-time vibrations. But if you add them together, then what happens is this. If you add them plus, then you get more. So, just in general, of course, in this case, it doesn't do as good as I want it to be. But if you have an electron and you add a photon, what you get is a higher state of wave particle being, so that the locality is more focused than if you look at the electron. So it's actually this should be more like concentrated in one spot. So, and the further you go here, then the lesser the lesser waviness you will see. But it's nonetheless wavy nonetheless. But what happens if you keep on adding particles together, then you get the wave aspect of wave particles is disappearing more and more, because you are adding waves together, and that's the relationship between quantum mechanics and macroscopic stuff. And so it may appear that a wave pattern is collapsing, but that's not what's happening. If you do a measurement, no, it's not collapsing. It's adding up to the other wave particles with which you take the measurement. I mean, the measurement instrument also consists of wave particles. And what you do is actually you're adding up wave particles, and that becomes more local and less wavy. in its behavior. So that's actually what I want to share with you. And that's why you notify with a macroscopic object, you detect lesser and lesser waviness unless you start adding energy and speed it up. Then it becomes more wavy again. So the quantum mechanical effects you are sensing the best when you isolate a wave particle, like an electron, like a photon, etc., like a proton. If you look at them individually, then you see the quantum mechanical effects of that wave particle. At the point that you are collecting them in a macroscopic object, then the lesser and lesser you will see the quantum mechanical effects appearing, because it's a big thing, and you add up the wave things. Okay, this is what I wanted to share. Oh, by the way, I'm presenting these thoughts on my new website. I have several websites, and it's I'll do it here. EK. .nl. EK. You can look either at www.ek sites excited .webklik .nl, or my main website is www.ek-sites.nl, and I will refer on this site. I will refer to that site too. So that's where I present these ideas, but also I thought to share this with you on YouTube as well. Okay, this is what I wanted to share, and the relationship between quantum mechanics and the macroscopic world. Okay, hasta la basta. Thank you for watching. See you next time.